This is lecture 5 for week 12 of CS 1030. And in this lecture segment, we're going to start to talk about assembly language. So we're basically done with machine language, and the next several lectures will all be about assembly. So as you've probably noticed, converting machine language operations to hex is error-prone and time-consuming. Reading the hex is not very easy or fun. Placing your data at specific addresses in RAM is not very good, is not very easy. Because, for example, if you make your program a little bit bigger to add some functionality to it, you might have to move all your data to different addresses. You might have to update a bunch of different places in your program. So the upshot is machine language programming is hard. It's not very easy. And if all we had was machine language, it would probably be impossible to implement something like a modern web browser. It's just too much complexity for that low level of abstraction. So we're going to start talking about assembly language, but before we do that, I just want to take just 1 minute to talk about what a programming language is. So a programming language is a set of grammar rules, a set of symbols, and a set of special words. And the grammar rules basically tell us in what order and what groupings we can put the symbols and words in order to make legal programs. So these rules about the grammar we generally call syntax. This is what things you can write down to make a valid program. And then the other part of a programming language is the semantics, and that says what the different things mean. It says what the different elements of the programming language mean. So like, what does a while loop do? What does an if statement do? So the machine language for the simple computer is a programming language. It's not a sophisticated one, but it's still a programming language. It has both a syntax and a semantics. The syntax then is, how do we write down an instruction? For example, what bits mean what? And the semantics is, what does it actually do? What does the instruction actually accomplish in terms of adding some numbers or something like that? So an assembly language is very similar to a machine language. And the way to think about it is, it has the same semantics as a machine language. It still has instructions, and the instructions do the same thing. On the other hand, the syntax is completely different. The syntax of an assembly language is quite a lot more like our pseudocode for a machine language than it is like the machine language itself, which is just the bits or the hex. So for example, in an assembly language, we get these sort of higher level commands. So if we want to use the ALU, we could use an add instruction. And an add instruction would say add R1 to R0 and put the result into R0. And that directly maps to a machine language instruction. So it's basically, again, just sort of a convenient syntax for a machine language that makes it easier to write programs. And before we continue on, I just want to give you a heads up that in your career, when you see assembly languages, sometimes the destination of an operation like this is at the right. So sometimes this is where the result of the operation goes. And sometimes the destination is at the left. This is where it goes. And sometimes different assembly languages for the same machine can have different conventions. And it's just kind of one of those irregularities that exist in the world, and you just kind of have to get used to it. It's not something we can sort of fix. Okay, so then the assembly language is this sort of slightly higher level version of machine language that has a better syntax. And there's a program that we use called an assembler. And the assembler is itself a program that turns assembly language into machine language. So let's look at how an assembler works. So what does the assembler do? It turns assembly code into machine language instructions. It turns labels into memory locations. And so let's talk about what labels are. So here we've said, load the variable A, or the memory location A, into R0. And here we have a label called A, and we've told the assembler that at the memory address specified by A, we want to initially store the value 2. So what that means is when we write this assembly language instruction, that's going to turn into a machine language instruction that loads into R0 whatever is at the address where A lives. So that address is not determined right now. That address is going to be determined later when the assembler runs. We don't specify it. It's sort of automatic. So that's what labels are. So it turns labels into memory locations, and this sort of makes it easier to figure out where things are because we can name, instead of A and B, we could use sort of longer words. We could come up with names that sort of mean something to us instead of like 13 or whatever. And so this gives us something that's a little bit like variables in higher level programming languages like Scratch. They're sort of not as powerful or as good in many ways, but they're better than referring to, address 13. And again, it's a super, super big advantage that the assembler figures out what addresses these labels live at, because what it's going to do is it's going to figure out how many instructions there are, and then it's going to put the data after the instructions. So now if we add some instructions to our program, when the next time we run the assembler, it's going to put the data at a different place. But the location where the data actually lives doesn't matter, and our program should just work either way. Okay, so another thing to understand when looking at these is, again, the destination of an operation goes on the right. So if we're loading here, we're loading what's at memory location A into R0. So that would be 2 in this case. Here we load B into R1. So after this instruction executes, R1 is going to contain the value 3. Now we're going to subtract R1 from R0 and put the result into R0, and then store whatever's in R0 into C, and then halt. So you can see that this program basically just performs subtraction on memory. So let's talk more about how assembly works. So here we have a program in assembly language. You write it in a text editor or something, and then you run the assembler, and it's going to produce the machine code. And the machine code should be exactly what you would have produced had you written the machine code yourself, corresponding to the assembly language program. So this is going to be a load instruction. Here's another load instruction. This byte is the subtract instruction. Then there's the store, and then a halt. And if you remember, A1 is halt always. That's sort of easy to remember. And now we have something different. We have the value 2, and then 3, and then 0. And these aren't instructions, of course. These are the memory locations associated with the labels A, B, and C. And C gets 0 at the start. And then the rest of memory doesn't contain anything, because this particular assembly language program didn't need any more than 8 bytes of RAM to store both its code and its data. So you can see that the assembler puts the data following the code. And it could have just as easily put the data at the end or something instead of the beginning, or instead of right after the code, but this is just where it happened to put it. So this is what an assembler does. It takes this prettier syntax for machine language and turns it into the actual sort of ugly old machine language, which again, you could have written, but it's nice if you don't have to. So how does this work? We're going to give you an assembler. It's a web-based assembler. So we'll give you a URL in Canvas, and you'll load that web page, and then there's a text field in that web page, and you type your program there, or possibly better, you type your program into a text editor and copy and paste it into the web page. And the reason that's better is because then you can save your file somewhere so you'll have it again. If you just type it into the web page and you close it, then you're going to lose it. Then you press a button on the web page, call it assemble, and that's going to create the machine code. You can copy and paste the machine code instructions from the web page into the Simple Computer 4. This is the one that is sort of a slightly more sophisticated version of Simple Computer 3. You enable simulation and then reset the simulation. So do the enable ticks thing in Logisim. And then you set the tick frequency to 1 Hertz or slower. And it turns out that the Logisim will sometimes get confused if you clock it too fast. So just don't do that. So set it to 1 Hertz or slower. And then you can mess with RAM if you want. You can edit the contents of RAM to, for example, change data values or whatever. And then you can set start from 0 to 1. The computer will execute. You set it from 1 to 0, and you can now, the computer is completely stopped, and you can figure out if it did the right thing. So differently than the previous one, this computer is going to go on its own. So it becomes harder to watch what's happening. You can still watch what's happening, but if you let it run freely, it'll be harder to see the intermediate steps in your program. So let's talk about what the assembler understands. What are the instructions we can do? So here, whenever we say RA, RB, or RC, we're just understanding those to be different registers. So whenever we see any of those, you should understand that it's referring to either R0 or R1. And you have to pick which register to use. The assembler doesn't do that. And L is a label that has to appear somewhere else in the program. So remember that L is a thing that's going to be turned into a memory address by the assembler program. So let's look at the kind of instructions you have. So you can store RA, where again, RA is either R0 or R1, into L, where L is a label. This moves the contents of a register into a byte of RAM. You can load L from RA. Sorry, I said that wrong. You can load from L into register A. you can move a value from register A to register B. And again, these could be the same register. You could move from R0 to R0. It's not useful, but you can do it. You can add RA and RB into RC. So RC is the destination register here. You can subtract RB from RA and put the result into RC. You could do an AND operation, an OR operation, a NAND, a NOR, a NOT. There's a clear operation. Clearing a register puts 0 into it, and you can halt the simple computer. So one thing you might have noticed here is that some of the operations in the assembly language don't actually correspond to machine instructions. So you've already seen all of the machine code instructions supported by this computer, and some of the things that we saw, like clear and not, don't exist. So what does that mean when you use a clear instruction, for example, in assembly language? What does that mean? Well, there's different ways to do it. The assembler could, for example, reserve a particular memory location containing 0 and load that into the register. Or it could also do something like subtract the register from itself, which is always going to get 0. The idea is it doesn't really matter to you. The assembler is going to pick a convenient way to clear the register. And again, the particular translation that it picks doesn't matter because it's going to have the correct effect regardless of what it actually does. And this turns out to be very realistic. Almost all real assemblers in the real world have these things which you call pseudo instructions. These are assembly language instructions that don't actually exist in machine code. And the assembler, again, just picks a way to implement it. It uses the actual machine code in some way to do the thing that it's telling you, that it's giving you an instruction for. And the reason we have these pseudo instructions is basically it's just a convenience. It's just to make things easier. And so as an example, many assembly languages have what's called a no-op, no operation. It's an instruction that doesn't do anything. And that instruction could AND a register with itself. But again, it doesn't matter how the no-op works. It's just understood that if you use a no-op in your program, the computer won't do anything with that instruction. It's just a way to delay the computer's execution for one cycle.